So, Professor, we are trying to start recording everything from now on. Okay, so the recording has started and we can begin.
Okay, well, hello, students. This is Andrew Charleson. I'm giving this lecture on the other side of the world, right down at the bottom of the world in New Zealand. And I'm very pleased to be able to give a lecture to you today. And I hope that my lecture will just complement what you have already learned about structures and architecture. Just before I begin talking more technically about structures and architecture, I'd just like to let you know that I retired from the university, from Victoria University of Wellington about 3 years ago. And for many years, I've been teaching in the School of Architecture there. And so I'm very passionate about teaching architectural students, and in particular discussing the structures of the architectural students' projects. When I joined the school, I came from a background of civil engineering. I had worked as a structural engineer for a few years. And then I joined the School of Architecture, and my first difficulty was finding research that was appropriate to architectural students. As you might imagine, most of the research that engineers do involves lots and lots of calculations and a lot of detailed consideration of materials like concrete and steel and wood. And I felt that that sort of research wasn't appropriate because architectural students aren't interested in the fine detail of their structures. I mean, after all, in the real world, architects let the engineers do the detailed design. And so what I set about to do was to undertake a research project sort of analysing structure from an architectural perspective. And so for 8 years, off and on, I did a lot of research for my book that was eventually published, titled Structure as Architecture. And in that book, I show the way structure, when it's used well in the hands of architects, can really enrich the architecture. And so one of my strong beliefs is that you as architects need to understand the structure of your building as a means of making your architecture richer, you know, giving it more meaning, more impact, making better spaces, and above all, using your structure to express your design ideas. And so that's really one of my passions, is that architects use the structure they need to actually communicate their design idea, their design concept, their design vision. And so in my lecture, I mean, I'm going to be talking mainly about earthquake resistance, but I want you to think about your own design projects, maybe the project that you're working on at the moment, and just ask yourself, you know, how can the structures that I'm hearing about today, how could they possibly help me bring my design, give it greater life, give it greater richness, give it greater ability to communicate my design concept through my design? And so I hope that you'll try and make that sort of connection always back to your design concept. I mean, it's no use designing the structure of your building if it's going to contradict your design concept. Because, as you know, architecture is about integration. It's about, bringing the different technologies together so that you can have an integrated design that aesthetically is satisfactory, it works functionally, and it also communicates your design ideas. And so in my first, I suppose, 10 years of working in the School of Architecture, that research project took up all my spare time. And of course, it is published now. I've now published a second edition of my book, Structure as Architecture. And I hope it will be like an inspiration for you to see how you can use structure to really communicate any design idea at all, and see structure as a friend and as an architectural element that you can use for your own advantages. And after I had worked on that book, I got to realize that there wasn't a satisfactory textbook for architects about earthquake-resistant design. And so the next few years was spent developing that textbook, Seismic Design for Architects, Outwitting the Quake, to quote from Frank Lloyd Wright. And this book shares my knowledge and my experience of designing earthquake-resistant buildings. And it's got the principles that all architects need to follow to achieve an earthquake-safe building. And these principles are quite easy to grasp, I believe. And I'm now going to take you through those principles by demonstrating this software called Resist. Resist is a rule of thumb software to enable architects to do the preliminary sizing of their structural systems to resist earthquake. And so now I think I will begin to demonstrate the software to you. And I'll pause at certain points to see if you have any questions. So first of all, this software can operate by us working from the tabs left to right. Could I please ask if you can see my cursor? Can you see me moving my cursor?
Yes.
Oh, good, thank you. So we start off by defining the building, and we've got, typically in every country, we've got a range of building types depending on the risk and also their importance to the community, especially following an earthquake. Like if we design a hospital, we'd have to design it for post-disaster functions. But I'm just going to design a normal structure today, maybe an office building. Could I just ask you students, for your current design project, approximately how many stories are you working with?
Three, Professor.
3. Okay. And what is the type of building you are designing, please? What's its function?
Hotel.
Righto, great, okay. So let's design a 3-story building. If it's a hotel, story height might be like 4 meters high. Your roof height, I'm saying 2.5 meters. Now, I assume in Macedonia that you build mostly in reinforced concrete. And so, like, that's a lightweight floor in wood. That's a medium weight floor using steel construction. And this would be heavy construction and reinforced concrete. So let's assume that this hotel is in heavy construction. The floor live load would be domestic because you've mainly got bedrooms. Let's assume that the interior walls of your hotel, well, let me ask you, what would the material of the interior walls of your hotel be? Would you use light construction or would you use masonry partition walls between bedrooms?
Light construction.
Okay, great. So let's have all the interior walls are lightweight. The exterior walls will also assume a lightweight, glazing and light wall materials. And the roof weight will assume it's a heavy roof, let's say a concrete slab on the roof. Now we come to the floor plan, and we model our building plan in this floor plan. And this software gives us the ability to add points and to create a polygon. And so we can make our hotel of almost any shape in the software. And you could use the software to model your own particular hotel project. And so let's say that this is the plan of your hotel. It's 40 meters long, and the width of it is 31 meters across here in the Y direction. The software puts in some preliminary structure, but we change that in a minute. And so let's just imagine that this is a rendering of your hotel building. And at the moment, you can't see any structure there. Well, you can see the floor slabs, that's all. And so I'm assuming that within this floor plan, you will provide columns and beams to support the weight of your floor slabs. Actually, you don't need any beams at all. You could just have a flat slab construction if you wanted to. And so what I'm assuming is that you have designed the gravity structure for your building. And so I'm assuming that for your particular building plan, you would be able to point to, say, rows of columns that probably support beams and floor slabs. And so it's likely that you've been able to do like the preliminary design of your gravity system, the floor slabs, the concrete floor slabs, concrete beams, and reinforced concrete columns. And if you followed the principles that you've learned so far in your course, then it's likely that your building will be, perfectly okay for gravity loads. And now I'm going to talk about making sure your building is safe for earthquake loads. So we go to the earthquake tab, and we've got to choose a hazard factor. Now, for my own country of New Zealand, we have a map giving us the factors for the different cities in the country. Like, I mean, I live in Wellington, and the hazard factor here is about 0.4. My guess is that for your city in Macedonia, I'm guessing that the hazard factor is about 0.3. So we'll go to 0.3. And we also have to put in the type of the soil underneath our building site. And I'm going to assume that the hotel we're designing is situated on medium soil. In other words, it's not rock, nor is it very soft soil, but medium. And so now I've done that, the software actually can start to work out the weight of the building and the amount of earthquake load that we have to design for. We can also design the building for wind loads, and there's a wind map for my own country, different wind regions. But because this is only a 3-story building and it's in reinforced concrete, the wind loads will not be critical. And so for the purposes of this lecture, I'm going to neglect the effect of wind loads because earthquake loads will be so much more severe. Now you'll see the building plan is sort of related to 2 axes. There's the x-axis and the y-axis. And so the first principle in earthquake-resistant design is that every building we design must have resistance in both the x and the y directions. We must always provide this resistance in both directions on both of these axes. So let's design structure to resist earthquake loads in the x direction. We'll do that first. Now I'm going to switch on the structure in the x and the y direction. And the default setting of the software is to start by putting in structural walls in both directions. And so in the x direction, this wall is resisting earthquake forces because it's strong in the x direction, and also that wall. And in the y direction, this wall will withstand earthquake forces, as will that one. So anyway, that's the default setting. And so this is what a concrete, and so in the x direction, we have a choice of structural systems. We can use structural walls, we can use moment frames, or we can use braced frames. So I'm going to use walls in the x direction. So I'm going to choose use structural walls, and I'm going to, and like that's what a reinforced concrete structural wall looks like. We've got a choice of materials. I can use reinforced concrete walls. I can use reinforced concrete masonry walls, or plywood or timber walls if my building is in wood. but let's use reinforced concrete walls. This is what a reinforced concrete wall sort of looks like. This is a concrete masonry wall using concrete blocks with reinforcing steel in them. And this is a plywood structural wall. So the next choice is to decide how many walls I want to use in this design. And so I go back to the floor plan, and at the moment in the X direction, I've got 2 walls, one here and one here. I can put these walls anywhere in plan. Of course, we try and keep the structure reasonably symmetrical, but we locate the walls relative to the function of the building and our design concept. So anyway, I'm going to assume that in this 3-story building, it suits the design concept to have 2 walls, one there and say one there, for example. If I wanted to, I could have more than 2 walls. I just need to right click, and I can add an element in the Y direction, in the X direction. So, now I've got a 3rd wall. Well, okay, let's put it over here. So, in fact, we'll end up with 3 walls, shall we?
Can I jump here, Professor, just to suggest to emphasize also the point on the center of mass and rigidity, if you can talk about these blue and red dots that appear. What are they?
Yeah, well, thank you for that question. And please do interrupt. I think that's a really good way for us to proceed. The blue dot represents the center of gravity of the building. I mean, essentially, it's like the center of the building plan. The red dot represents the center of rigidity or the center of resistance. Now, if I make my structure symmetrical about the way like this, I can make the center of resistance at the same position at the center of gravity. But we always try and have these dots fairly close together, but they don't have to be too close. It's okay to have some torsion in the building, but we don't want it to be too excessive. Let me just delete this element. And if I bring this to here, you see now we've got a perfectly symmetrical building in the X direction. But I will add in that extra wall, and I'm going to put it, as I said, somewhere about there. Oh, well. Okay, so now I go back to the tab, lateral structure in the X direction. And now I have to choose what the wall length will be. Now, I think those walls could be a bit weak. So I'm going to increase the length of them, say to 6 meters there. And so this is my first design. In the X direction, 3 walls, 6 meters long, and they probably only have to be 20 centimeters thick. Right. Now I'm going to design my structure in the Y direction. And in the Y direction, I'm going to use moment frames. And this is what a moment frame looks like. It's a pretty boring building on my own university campus. But you can see the very highly expressed moment frames, columns, beams, and rigid joints. And so if I want to, I could resist all the earthquake forces on our hotel with just 2 moment frames, one here and one here. Well, so let's try that. So I've got 2 frames. Now I can choose how many bays per frame. I'm going to have 3 bays. You see, you can choose as many bays as you want to suit your architectural concept and your building function. I've got 3 bays now. The distance between the columns is 6 meters. Each beam supports 8 meters of floor slab. Now the columns look very skinny to me, so I'm going to make them quite a bit heavier. 600 millimeters is the depth of the column now. So this is my first design. Now I need to
can you hide that button, Professor? You can just press the hide on that window that you just moved.
Oh, right.
Yeah, hide.
Yeah.
Yeah. So
Thank you.
better. Okay.
Okay. So now I've done a design and I go to results. Now, first of all, in the upper part, we've got the results in the X direction. And what I have to do as the designer is to make sure that all these results are less than 100%, because that 100% represents what is allowed by the building code, which
The capacity.
Yeah, it shows, I suppose you could say it's the demand of the building code. So at the moment, if we look at the earthquake ultimate, it tells me that the shear force,
Lower than the capacity.
that's right, the shear forces are 62% of the capacity or the strength.
Demand of the capacity, yeah.
Yeah, and the moment demand is 59% of the capacity. And the
percent over the capacity.
Pardon? Like this is the oh yeah, it's the demand. Yeah, this is the demand. And this is the capacity. So like this is telling me that the shear strength is, sorry,
Drift is 50% the demand.
the drift is 50% of the code allowable drift. So our building codes allow for buildings to move sideways a certain amount.
Yeah.
And so at the moment, this building is moving sideways 50% of the maximum allowed by the code. So these figures mean that the walls I've designed are stronger they're stronger than they need to be, and also stiffer than they need to be. So I can go back to the X direction and I can reduce the wall lengths. There, now it's starting to fail. See, if I make the wall 3.5 meters, the wall fails because the drift, the sideways deflection in an earthquake is greater than the code allows. It's in fact 140% of the maximum that the code allows. So the structure is failing. Therefore, I have to go back and increase the wall length to 4.5 meters. And now those walls are strong enough and stiff enough. And actually, I finished my design. If I click other results, the software tells me that the walls, the structure is separated by 99% of the building width, which is acceptable. In other words, there's very good torsional resistance with this structural layout. It also tells us that we are allowed to have penetrations in these walls, but they're only allowed to be up to 15% of the wall length at ground floor level. And we're also told about the foundations. We're told that we could use some square pads, 3.3 meters square, but we also need to have some tension resisting piles. And these piles have to be 450 millimeters in diameter, and they've got to have bulbs or bells at their bases to provide the tension resistance to stop the walls from overturning. And finally, I've got a red line here telling me that the minimum thickness to prevent the wall from buckling in an earthquake should be 230 millimeters. And so that tells me I've got to go and increase my wall thickness to 230 millimeters. And if I just go back to my other results, yeah, I'm okay. So now I've finished my design in the X direction. Everything is looking good. Now we look, or let me just stop and see if you've got any questions or comments about my design in the X direction.
Professor, I have a question.
Please.
What happens if we use walls with different dimensions or rectangular columns?
Yes, well, that's a really great question. In the software, we are forced to use walls of the same dimensions. So if in your design you want to vary the lengths of your walls a little bit, then you would put in the average length that you are using in your design. You know, the average length. And regarding columns, we're assuming that all the earthquake loads are resisted by the walls. So that means that all the columns you are using to support your floor slabs, those columns can be quite slender because they only need to withstand the gravity loads. Because the earthquake loads are resisted by the walls. Is that okay?
Yes, thank you.
Any other question? All right. Well, let's look
and I think this should be clear. Lateral stiff.
I'm sorry, could you please repeat that comment, Isaac? I'm sorry, but I cannot hear anyone speaking. Can you hear me still?
Yes.
Okay, well, let me continue then by looking at the structure in the Y direction. And immediately we can see we've got problems because we've got fail. Wherever we see red means that the structure is inadequate. And so for the ultimate earthquake situation, we can see that the bending moments, the bending capacity, the bending demand is 137% of what the code needs, and the drift is 162% of what the code allows. So basically, my 2 moment frames are too weak and they're also too flexible. And so I've got to go and my first attempt is to make my members larger. So if I increase the column depth there to 75 centimeters, those 2 frames are sufficient. And so if I just go back to results again, see everything now is under 100%. Everything is okay. I click on other results. It tells me my torsion is not a problem. It tells me my column depths are 750 millimeters. And the width of the column is 450 millimeters. So these are rectangular columns. And the beam dimensions are 750 millimeters deep by, say, 400 millimeters wide. And there's information about the foundations we require. So I have now done a design for this hotel where in the X direction, all the earthquake loads are resisted by 3 structural walls. And in the Y direction, all the earthquake loads are resisted by 2 moment frames. And most of the gravity loads of the building can be resisted by quite slender reinforced concrete columns supporting beams and or floor slabs. So this is one design. And then, and so just let me show you, we could say, well, let's use cross bracing. So instead of the structural walls. So if I go to the X direction, oh, sorry, I've chosen the Y direction by mistake. So if I go back to the X direction, and I choose braced frames, see immediately I have these 3 braced frames. I'm going to just use 2 of them. So I'm going to remove this braced frame. I'm going to go to the X direction. Now I'm going to design these braced frames. I've got a choice of the different types of braced frames. Like, for example, like that's a wooden braced frame under a house. This is a steel concentric braced frame. This is a structural steel eccentric braced frame because the diagonals don't meet at a single point, but there is some eccentricity between them. And then here we have a concentric braced frame. Here are the steel braces, like diagonals. And then finally, and I think you might recognize this building, the Pompidou Centre. Its resistance to lateral loads comes from these steel tension only bracing. And maybe, yeah, that's all we need to know. And so I'm going to use concentric bracing in this building. I'm going to have 2 bays of bracing. I could have as many as I want to, but say 2 bays suits our design concept. The bay length 6 meters, that's okay. The floor width supported by one of my beams is probably more like 4 meters. And now I've got to increase the brace size, the size of the braces. So I'm going to make them, say, 0.4 meters in diameter. And I go to the results. And here are the results of my steel cross-braced frame. The braces are working at 50% of the demand on them. And so I've greatly over-designed my structure. I mean, it's wasteful. I'm wasting so much steel. And look, the building is incredibly stiff. The drift, that is the amount it sways sideways, is only 9% of what's allowable. So my building is very strong and too stiff. I'm wasting material. So I go back to my tab in the X direction. And first of all, I'm going to just have 1 bay per frame. So I'll show you. See, at the moment, I've got 2 bays. I'm just going to have 1 bay per frame. There. And I go back to my results. And now the brace is working at 88% of the demand. So, no, sorry. What I mean is the brace is working at 88% of the brace is catering. The brace is under the code allowable, and it's only operating at 88% of its capacity. And so this means that the brace is very economically designed. The building is still too stiff. The drift is only 24%, but I really can't do much to, I suppose this tells me that my bracing is too stiff. And so what I can do is I can make the bracing, I can reduce the bay length, say 4 meters. Now let's see what happens. Now my drift goes up to 28%. My brace is working so that it's at 78% of its maximum capacity. So I can reduce the size of my brace to say 0.35. Yeah. And now I've done a design. And so if we wanted to, this would be our preliminary design for our building. 2 steel cross brace frames like this, and 2 moment frames at either end of the building. So I'll just pause and see if you have any questions you'd like to ask me about what I've demonstrated so far. Righto, well, let me continue by just saying that if we want to, we can integrate the gravity resisting system with the earthquake resisting system. And so, like for this particular building, we might do that by adding in additional moment frames. I just right click. And so, and I could, yeah. So say I've now got, so say now I'm integrating the gravity resistance with the earthquake resistance in the Y direction. And so now these moment frames I've provided, they will also support the floor slabs. Now I have added, now I've got 2, 4, 6, 7 frames. So if I go to the Y direction, I've got 7 frames. The results are down here. So because I've added all those additional frames, the frames are only working at 40%, 33 or 40% of their strength, and the drift is only 45%. So clearly I can reduce the size of my columns and beams. And so I'm going to just reduce the column depths from 0.75 meters to 0.765. No, I've got to go to 0.55. So by putting in all these additional frames, I've considerably reduced the sizes of my columns and beams, you know, to get a more cost-effective design. And so now with this design, as I've said, the frames will carry most of the gravity loads, and as well as that, they will be resisting the earthquake loads. Now, one of the principles, another principle of resisting earthquake is to make sure that we have a good amount of separation between our earthquake resisting elements. And I'm going to explain that by going back to the floor plan. Like at the moment in the X direction, the 2 braced frames, they are separated by the width of the building. I mean, if we wanted to, we could indeed bring these frames into the inside of the building like this. Now we are reducing their separation, and the building is torsionally not so strong. just by way of an extreme example, if I bring them right into like the core of the building like that, and we go to results, you see we get a red flashing light on other results. Something is wrong. And it tells us that the problem is that the separation between the structures in the X direction is only 18% of the building width. I must adjust it until it's more than 25% to give that greater torsional resistance. And so what I've got to do is if I've got to stretch these out a bit more, and now that design's okay. But yeah, that's about the limit. Now, because these brace frames are strong in the X direction, the frames can go anywhere in plan, pretty much, as long as they're not too close. But now I've moved them closer together, they fail. The brace is failing. But if I reinstate them to the perimeter of the building, then basically the design is sound once again. It's failing just ever so slightly. So I need to go back and just increase the size of the brace a fraction, say 0.37. No, 0.4. There. And so now I go back to my 3D model, and that's the structure to resist earthquake for our design. So I'm hoping that you students might be able to do a quick model of your design project in Resist and come up with the approximate structure you need to make your building earthquake safe. And I think with this demonstration I've given you, you might be able to do that reasonably easily. So I'll just pause again and see if you've got any questions. I mean, perhaps you would like me to investigate some other structural options. Please let me have your questions or comments. Thank you.
Professor, I wanted to ask if bracing behaves better than walls, or I didn't understand that.
From an earthquake engineering perspective, walls are the best and safest structural system. So I would always recommend students and architects use structural walls to resist earthquakes. But say, for example, your design concept was about transparency, then walls may not be a good solution. And, cross bracing might be better. And so bracing can be designed and built to be safe. And so if bracing is better for articulating your concept, then that would be the better choice for you.
Another question would be the lateral resisting systems like walls and braces. would they be more effective to be placed on the core of the building or on the periphery, perimetrically? What is the most effective position?
The most,
so that
I'm sorry, the most effective position is definitely on the perimeter.
why?
Because the problem is, if you put them at the core, your torsional resistance becomes greatly reduced. Let me demonstrate. I'm going to delete a lot of these frames. Right. And I'm going to move these wall. Oh, well, so let's just look at the results first. So I've got to increase my, I've got to go back and increase my column depths. 0.75, which is what we had before. So if I bring these, well, first of all, if I bring these frames near the core, we get the problem with torsion. And if I bring these walls in, you see, the structure in the core is not good for resisting torsion. And also it gets more highly stressed. So like you'll see that now I've brought these elements into the core, they fail. You know, they're not strong enough. The brace isn't strong enough, and the moment frames are not strong enough. And so if your structure resisting lateral loads is in the core, yes, your building is far more torsionally flexible and it's more torsionally unstable. And so the principle always is, if possible, have your structure towards the perimeter. It doesn't have to be on the perimeter, like, you know, it could be one bay back, but at least when your structure is separated, it's far more effective in terms of torsion resistance.
Because we have increase of the moment arm between.
The distance between the moment arm between these two frames is quite large now. And the moment arm, the separation between these walls is large. And so that is the optimum structural layout. But let me just go back to the Y direction and design some walls. So now I'm using walls in the Y direction. I have to make them a wee bit longer there. So going back to the floor plan, these are structural walls. If I bring them into the core, I mean, I can design that. I could do this as a design. So my structure is pretty much in the core. And then that means around the perimeter of my building, I can have these slender columns and beams just supporting gravity load. But this building will not perform as well because it will rotate torsionally and more, and therefore it's likely to suffer greater damage than if the walls, you know, were near the perimeter. So yeah, the principle is try and keep your structure nearer the perimeter if you can. Are there any other questions or comments, please?
Yes, Professor.
Please go ahead.
I wanted to ask that I know that brace frames are used in the construction of structures, which are subjected to lateral loads. But my question was, can we use moment resisting frame? Because also moment resisting frame perform the same function, which is resisting lateral loads and seismic loads and providing stability. Because there, as I know, brace frame system is mostly used in the construction of steel and timber structures. On the other hand, moment resisting frame are mostly used on reinforcement construction.
Yes, that is true. In reinforced concrete construction, we usually use either moment resisting frames or reinforced concrete walls to resist our lateral loads. And so in my first design I did in the Y direction, you know, I showed you my design using moment frames. You know, that was the design we had, just with 2 moment frames. So yes, moment frames are very suitable for resisting lateral load. And, you know, by all means,
I might add here also the parameter of the building height. So the moment frame system is effective for certain amount of building heights up to some certain point, and also by the length of the base between the columns, the spacing between the columns. And of course, when going higher and higher with buildings, then we are imposed to use additional lateral resisting mechanisms, either and the question would be, how high can we go by using only moment resisting frames? This is another question which really experienced engineers are best suited to give this kind of answer.
Well, that's right. Well, I mean, take, for example, if I go back to the Y direction, like here's a 12-story, about a 12-story building, just relying on perimeter moment frames. Actually, there's no limit to how high a building can be using moment frames, in my view. I mean, some of the tallest buildings in the world use tube construction. And I mean, a tube construction is just a moment frame with very short bay lengths. Like, see, I'm creating a tube construction here. And so this could go up to 20, even 50 meters. For example, you know, the Twin Towers in the States, I think relied on steel moment frames forming a perimeter tube construction. So I don't think there's any limit on how high you go using moment frames.
But I think eventually you have to turn to steel, continuously increasing the building height. You have to put structural steel.
I mean,
because of also the compressive capacity. So you have concrete like 40, 50 megapascals. On the other hand, you have 500 megapascals steel. And if you mix them together, that's when you push the boundaries to these. I am sharing my view now from my point of view, because moving like 400, 500 meters and above, you have to introduce a new, stronger material.
Yes, I would agree. I mean, it's possible to do it in reinforced concrete, but the members would be so large
Yeah,
that they would affect.
And the load would be so high.
Yeah, that's right. So, but do you know the building in Taiwan, Taipei 1?
Yeah.
I think, is that reinforced concrete or is it concrete within steel sections?
I'm not sure.
I'm not sure either. But anyway, I agree with you. Composite construction is usually the
optimal solution.
Yeah, that's right.
Professor, on the other hand, I wanted to add something. Moment resisting frame are mostly used on reinforced concrete structures, but on the other hand, the analysis of the connection is more complex. It's expensive to construct, and the method of stabilization is not as good as braced frames, because we know that the purpose of earthquake engineering is not to build strong and earthquake-resistant buildings that do not experience the slightest damage in rare and severe earthquakes. So the cost of such structures for the vast majority of users will have no economic justification. Instead, I believe that engineers focus on buildings that resist earthquakes, effects, and do not collapse. So if they are used expensive, if a moment resisting frame are expensive to construct, and the other hand are more complex, and on the other hand, the method of stabilization is not as good as braced frames, why it's such common to use these moment resisting frames to reinforce concrete structures?
The reason is very simple. It's because moment frames are easier to integrate with the architecture. You know, a moment frame is able to be integrated into the building function, usually a lot easier than a braced frame. And it's because architects like the ability of a moment frame to be integrated in with their planning and their aesthetics. This is what drives the use of moment frames. It's purely driven by architects. Like the engineers would prefer that architects use structural walls to resist earthquakes, because structural walls have a far better track record of survival in earthquake. But structural walls are problematic because they affect the function, don't they? You know, they affect your spatial planning. Whereas moment frames are much more flexible and are much easier integrated in with spatial planning. So it's architects who are driving the use of moment frames.
Beautifully put.
I mean, my personal, I mean, I agree with your comments that, you know, you, the student, have made. I agree that moment frames are quite expensive, and actually they're very sophisticated structural elements. And they're very sensitive to construction mistakes and errors. And so, you know, they're very, they're sort of rather fragile, and they haven't got a good track record actually in damaging earthquakes. But in spite of that, us engineers, I mean, basically we are your servants. Engineers are the servants of architects, aren't they? And so we engineers, you know, we want to give you the structures that best suits your concept and your building function. And that's why, you know, we do our best to design these moment frames for you.
Mm-hmm. I think this discussion is. I really love the questions in the end to wrap it up somehow, and at least to draw a global picture with the relation between architects and structural engineers, and also to give a general overview to architecture students of the challenges that we as structural engineers are tackling every day. So I think, Professor Andrew, this was a wonderful presentation of the software, and I'm very happy that between this presentation of the workflow of this software, we also had a chance also to do some general discussions about aspects concerning the structural resistance and stability from earthquake forces. I don't know what is your plan. Did you have any other thing in intention to present, Professor?
Well, I'd just like to say that, I mean, my intention has been to use this software to really demonstrate structural principles that you architects can use in your
one
project.
question about the software, Professor. Are we able to get this software so we can play with it during our research and studies? How we can how we can secure this program for our needs?
Yeah, well, this software is free on the internet for you.
Mm-hmm. Where can we get it? Can we?
If you Google the New Zealand Society for Earthquake Engineering, and then you just search for resist, you can immediately download the software for free and start using it.
So that's easy.
It's very easy. Can I just mention one final?
This is wonderful.
I'd just like to mention one final point. Is that okay?
Yeah, yeah.
When a student has finished their design, you click on the reports tab and you click on the architectural report. And this is a 2-page summary of the results of your design. And this report can be like the proof that your design is safe in an earthquake. What you do is, before you print the report, you go to the 3D model and you orientate your building so that the structure is very visible, say like that, and then you click on image and you say set image for report, click, and that picture will appear, automatically be printed out in your architectural report. And then you've got a good little hard copy of proof of your design that you could show your tutor. So look, that's all I want to say. Thank you.
Thank you, Professor, for your time and beautiful presentation. I would also like to add from my point of view that this software is very easy to use and very beneficial for students during this research phase. And I would also recommend them to get this software, to download it. And even I commit that next week, when we will hold the next lectures in faculty, because from next week we are beginning to give classes physically in the faculty. We are moving now back to normal slowly. So I will try to present to you a new structure, how we design it, and we will embrace this approach so that you can use this software in order to give the solution of the building, and even we can use it also during our exam. So we will make a further discussion next week about this. And also I want to tell you that Professor Andrew, as he mentioned before, he has written, excuse me for a second, please. What I tried to say is that Professor Andrew is also the author of the book Seismic Design for Architects, a book that we have presented in the beginning of this course. Some of you have also bought this book, and I strongly recommend you to read it because it goes perfectly hand in hand with this software and what we are teaching during this semester. So I really want to thank you, Professor, for your time to share with us this software, and also, I mean, your contribution for us is very significant, considering also the availability of the book now that we have in Albanian, and also the software is available for free. I think the students should use this opportunity and to grasp as much knowledge as they can during this course.
Isaac, can I just say one thing to you, please?
Yes, yes. Please.
If you click on the earthquake tab, you'll see that you've got to put in what the hazard factor is.
Yes, yes.
And so could you please, this hazard factor, that is equal to the
PGA.
The PGA.
Yeah.
Exactly, for say a 500-year return earthquake.
Yes.
On PGA
with
on
10% probability of exceedance in 50 years or occurrence of one earthquake in 500 years.
That's correct.
Yeah, that's the standard. Yeah.
So could you please just advise your students as to what the hazard factor will be, you know, for your own location?
Yeah, actually we have a map printed on our faculty environment, in the corridor, in the hall of our faculty. We have a big map of the Mediterranean with this hazard factor, and I will suggest them there to look out for the terrain that we have. So it is actually 0.45.
Oh, fantastic.
Yeah, it depends on which location.
Yeah, of course.
So so the map really is very explicit about this, and It is a serious study which has been done by the European Union with this SHARE project. And really you have there the entire Mediterranean region. And you have this hazard factor just printed there in color. So this is a great thing, but especially I love the idea of generating reports. So you model preliminary the building, you give some initial solution, and you generate the report, and you as a student, you can make a discussion about the results printed on the report. And that's how also you can show your knowledge about this field. I think we can implement this software inside our curriculum, inside our course. That's why I say this is very important, and for architecture students, they really should use this opportunity. And I strongly recommend you to read the book, because now it is also available in our language. And I am happy, Professor, just to introduce you and for the students to be aware. And the author of the book that we are using is today holding a presentation right in front of them. If you have any other question, feel free to ask. I don't know, Professor, how much time have you planned? I don't want to take your time. Well, I don't know the time difference now. It is very. What's the time in New Zealand now?
It's just after 8:30 p.m.
It's night.
That's right.
8:30 in the evening. Yeah. So I would ask the students to consider this time difference and not to linger you any longer. Not to take your time. I presume it is late already. Personally, I really want to thank you, Professor, for your time, and I enjoyed your presentation. And also, I wish we will have future opportunities in the future. Perhaps if this pandemic thing goes slowly away and things go back to normal, perhaps we can invite you also to our faculty to participate for a week or two. I would be glad to consider this.
Yeah, well, option. I mean, I would love that. I've never visited Macedonia, and I'd really love to come and visit one day. So let's hope that might happen in the future.
I'm looking forward to it, Professor. Students, do you have any other question?
No, Professor.
Well, we are recording this video, so if you have any question about the presentation, you can repeat the video again. Professor, I leave the last words to you.
Okay. Well, let me just say that I haven't explained to you what is in the help section of the software, but there are several documents in the help section. One document gives the assumptions that the software uses. Another document gives the full engineering calculations, which of course are not relevant to you. And another document gives a step-by-step tutorial to guide you in using the software. So if you do need help, please refer to that information. So finally, I'd just like to say thank you for inviting me to make this presentation. I've enjoyed sharing my enthusiasm for the subject with you. And I wish you very well in your studies. And I'm very happy for Professor Isaac to contact me if you've got any questions that you'd like me to help you with. So I'll just say good night from Wellington, New Zealand.
Thank you, Professor. Thank you. Looking forward for our future discussions again. So my my thanks, many thanks to you, and wish you good health, and see you as soon in the future.
Indeed. Thank you very much. Goodbye, everybody.
Goodbye, Professor.
Goodbye, Professor.